Time for parts. So we've sort of talked about some of the things can go wrong. In this part of the talk, I'll focus on differential privacy, which is sort of one framework for trying to write down a property of a set of algorithms that prevent the kinds of attacks we were discussing before. Okay? And it's very closely related to membership inference attacks, although it predates that terminology by a decade. So differential privacy is this sort of notion that there's like a restriction on the algorithm that processes the data. There are lots of current deployments. They start, the big ones, like high-profile ones, first ones were at Apple, at Google, and at the US Census. But at this point, there's a whole ton of them at companies, by statistical agencies, at governments, things like Wikipedia. And there's actually a registry of these deployments run by OpenDP, which is this, OpenDP is like a open source software project based at Harvard for software for differentially private systems. So the registry is really nice. It captures a bunch of dimensions to the deployment that are really interesting. And there's this whole field of research that this has grown into with like lots of intersections with other areas of research. We're not going to get into that in any real detail. OK, so what's the definition? The idea is the following. We're going to write down a condition. We want to write down a condition that is sort of broadly usable. And so we want it to be a condition just on the algorithm and not on the data per se. Okay? So for the purposes of defining things, we're going to think of our data set as some like fixed object, which is a list of n records for now. We'll take the simplest setting. And each record lies in some domain, and the domain can be anything. It could be numbers, it could be tax forms, it could be email, text, whatever. For now, we're going to think of x as fixed, and we're going to think of the algorithm that processes x as randomized. And so what this means is that for every data set x, this a of x is a random variable that has a distribution, well-defined distribution. Okay? And it's the properties of that collection of distributions that we're interested in. Okay, the randomness might come from adding noise. That's going to be our main example today, but there are other types of algorithms that make sense. Okay, and the basis of the definition is a thought experiment where I'm going to imagine changing one person's data, or maybe adding or removing a person from the data set, depending on the exact setting. And I'm going to look at how the random variable a of x, how its distribution changes. So we're comparing the blue world to the green world. In the green world, one person's data is now different, right? So I've got some distribution in the blue world. It's some arbitrary distribution in high dimensional space that looks obviously like this. And now in the green world, I get some other distribution. And the kind of question I'm asking is like, is there any set of outcomes whose probability differs significantly between the blue world and the green world, right? So this could be, for example, the set of outcomes that lead to me getting denied health insurance, right? So what I want to make sure is that that set of outcomes doesn't change significantly, it doesn't become significantly more likely when my data are actually used. Okay, so mathematically, we'll say two data sets are neighbors. For now, in general, if they differ in one person's data, okay, which for now is just going to mean like we're going to think of it as like one row of the data set. And so the requirement is that neighboring data sets induce close distributions on outputs. And formally, we're going to capture closeness with a parameter, or sometimes a pair of parameters, which we call, for now, just one parameter, which we call epsilon. And the definition goes like this. For every pair of neighboring data sets, and for every event in the outcome space, or any measurable subset of outputs, the probability of this event occurring when the true data is x, let's say without my real data, versus the probability that this occurs when my data is used, those should differ by a small multiplicative factor. Okay? And the size of this multiplicative factor is controlled by the parameter epsilon, and you should think of it as sort of 1 plus epsilon, although it's mathematically convenient to work with e to the epsilon. Okay. When epsilon is small, these are more or less the same. When epsilon is big, they're not. For various reasons, we often need to give ourselves some slack in this definition. So we'll think of this epsilon as like a leakage measure. It's a measure of how much we're revealing about individual records. For various reasons, we'll often need to add an extra term, an additive term, which we'll use the letter delta for. So this becomes now epsilon delta differentially private. But we'll think of this delta as sort of a very small term. Our dependency on delta will be logarithmic in one over delta, various things. So we can sort of crank down delta without hurting things too much. Epsilon is going to be the main driver of the complexity or the accuracy of our algorithms, although both come up. Okay. So this is the definition. Actually, just quick question. How many people have not? Raise your hand if you've seen this definition before. OK, we're going to move very fast. All right, great. OK, so one way to achieve this is by adding noise. That's going to be the one we have in mind. And the sort of like a useful starting point, by no means the only method or the most sophisticated one, is to calibrate the amount of noise we add to something called the global sensitivity of a function we're interested in releasing. So suppose we've got some function f. It might be a high-dimensional object. So f maps my data universe to maybe some dimension d. And now I can figure out how much noise to add by asking how sensitive f is to changes in its data. And so the global sensitivity is the maximum over neighboring data sets of, in this case, the L2 difference between f of x and f of x prime. Okay? And depending on whether or not we use what norm we use to measure the change in f from f to f prime, we get slightly different results. For today, it's easier to, I think we'll just stick to L2 because that's the easiest one. So for example, suppose my statistic was a one-dimensional function that was just like the proportion of diabetics in the data set, then it would have global sensitivity 1 over n, because the proportion of diabetics can go up or down by 1 over n when one person's data is changed. Okay? And in general, averages of bounded quantities behave very nicely. Other things, it varies. Okay, but the overall image is that this global sensitivity measure, it's a Lipschitz constant, if you will, but it measures like how much the function f stretches apart or pushes together neighboring data sets. Okay, and the basic result is that if the standard deviation per entry is calibrated to this global sensitivity, then we get a differentially private algorithm. And actually, to make this a little more precise, there is this log 1 over delta term. I said delta is there. And it's necessary for the L2 version of this result. If the standard deviation, the entry, so the point is that I add more noise when the global sensitivity is higher. I add more noise when epsilon is small. And then I add more noise when delta is small, but that dependency is much weaker. Okay. And the picture you should have in mind for why this thing is true is that when you go from data set x, if you're adding noise to f of x, when you go from data set x to data set f of x prime, you're considering two, let's say, Gaussian distributions, if we're adding Gaussian noise, that have been translated relative to one another. They have the same covariance structure, in this case independent, it's isotropic. Same covariance structure, but they've been translated relative to one another by f of x minus f of x prime, so by at most the global sensitivity. And so basically what I'm doing is asking for some bound on how easy it is to tell apart two Gaussian distributions with the same covariance but whose means are different. And it turns out that's a well understood, easy to think through question. Okay, so that's this sort of basic mechanism. So let's just run through one example that I think is useful to connect to our earlier discussion. Let's say I've got a bunch of points in space and I want to release their empirical mean. Okay, so here I've got a collection of points. These are my data points. They've got some mean, which is their average, the centroid, in d dimensions. And let's assume they all lie in some known ball of radius 1. Okay, that makes our lives easier. It's not strictly necessary. Now, if I think through, like, how much can this mean vector move when I change one data point? Well, the mean vector, the mean is 1 over n times the sum, and so the mean can move in L2 by at most 1 over n when I change one of these data points. Okay, like imagine sort of one of the terms in the sum here changes, right? And so as a result, I can add noise with standard deviation about 1 over n per entry. And I will get a point that is not too far from the true mean as long as the dimension isn't too big. So how far away do I wind up from the true mean? My distance from the true mean is now about 1 over n per entry, but in total it's about square root of d over n. Okay? And it turns out that this is sort of like, this mechanism is exactly matched by the type of membership inference attacks we discussed in the previous section. Even though things are sort of normalized a little differently, because here we're talking about real data points, it turns out that I scaled things so they compare. So any mechanism that releases a vector that is much closer to the mean than square root of d over n it admits a successful membership inference attack, regardless of how the mechanism works. And vice versa, if I'm willing to tolerate more error than that, if I'm willing to tolerate error square root of d over n times a small multiple, then I can design an algorithm that's differentially private. Okay?
Here, the data is uniform?
So here there's no assumption. OK, so for the upper bound, there's no assumption on the distribution of the data. It's a worst case statement. The lower bound is for data that's uniform in the ball, let's say. Or just normally distributed or something like that. Or uniform in a sufficiently large ball or something, yeah, along those lines. OK, and so good. And so that's just to sort of connect this that like, now, why is this interesting? Well, if we think about what this definition is telling us, it is this definition, if I go back here for a second, it is in some sense about resistance to membership inference. Okay, what this definition is saying is that if I, in this case, in this setting, I'm comparing two data sets, and we're saying that even someone who knows the two data sets, so he knows the entire data set X and knows how one person's data might have been changed. So they're given like all n minus 1 other data points and given two candidate versions of my data, can't figure out which of those two candidate versions was being used. Okay. And so there's sort of a sense in which these sort of membership inference attacks are like the contrapositive of, not the contrapositive, the negation of differential privacy, although the membership inference attacks we saw earlier don't require knowing all the rest of the data. They just require knowing its distribution. Yeah. Yep, no, go for it.
But another significant thing is whether you take the data to be from a population or not. Right? So in particular, here you're taking the GS to be the worst case. And if I know that the GS holds only with high probability.
Right, so there are
How would
some, okay, so we could talk, maybe let's take it offline. The short version is, depending on exactly the high probability, type of high probability bound you have, you can often make use of a high probability bound, but then your algorithm will only be accurate when the data is correctly distributed. When you get data that doesn't follow the distributional assumptions you want, the algorithm might just throw up its hands and say, no, I'm not producing output or something like that.
Okay. Okay. So that's a very strong thing. So you're saying that because if you look at the GS, I mean,
Yeah.
I look at the GS and I see generalization, and it's exactly a generalization quantity. So if you have something that generalizes, and generalization is always just with high probability, right? It's not worst case. Then you can that generalization is guarantee is enough to turn it into differential privacy.
Yes, up to factors of the dimension.
Dimension. There's no dimension here.
Yeah, there is, right?
Why?
So I'm adding, the global sensitivity accounts for changes in all d coordinates, and I'm adding that much noise in each coordinate. So in many settings, that's sort of costing me a factor of square root of d.
Oh, you need, I see, because you need this GS, you have to measure, so it's the output and it has to be a vector you're measuring in L2.
Right.
So that's, okay, so that's where the first.
So, and that's in some settings unavoidable,
Okay.
right? And some settings more avoidable.
Okay. But you could, but you can actually have all this just with respect to population. You don't really need worst case.
Yeah, with some caveats, but yes, yeah, that's right. Okay, so let me just talk a little bit about like how we should think about what this definition is giving us in sort of real context, right? So a naive hope, okay, here's the kind of thing especially if you grew up in like, if you ever took a crypto class, I don't see any like crypto type people here, but if you ever took a crypto class, you would see a definition of encryption that looks something like this. After you see the ciphertext, your beliefs about the plain text will not change. Okay, that's sort of roughly speaking the definition of a strong encryption scheme. So we might hope for a similarly strong promise here that like if my data gets used by some differentially private algorithm, then your beliefs about me will be the same after seeing the data as they were before you saw, after seeing the output of the algorithm as they were before seeing the output of the algorithm. Okay. So it turns out that's impossible to achieve, and I'm gonna, you can prove this mathematically in various ways, but I'm gonna give you this proof by story. Suppose that you know that I smoke, okay? This is like you know this a priori because you walked out of the Simons Institute and you saw me out there on the sidewalk with a cigarette in my hand, right? Then you see a clinical study that tells you that smoking and cancer are correlated. And assuming it's the 1960s, first episode of Mad Men, and we didn't already know this to be the case, you were surprised by this, and suddenly you have learned something about me, right? You have learned that I am a terrible health insurance risk. But that thing that you learned about me was sort of something you learned because of this clinical study. The output of this clinical study taught you something about human health. It wasn't because my data were used in the study. So what differential privacy implies is not that you learn nothing about me. It's that no matter what you knew ahead of time about me, you will learn almost the same things about me from the output, whether or not my data were used. So it's a very different type of claim. Okay. Now, it is strong enough to provably prevent the kinds of attacks we were talking about in the previous section, up to this epsilon term. But it tells you that it tells you that the sort of guarantee is kind of relative to what you would have learned without my data, and that's unavoidable if you want to tell people interesting things about the data, right? That's the point of the example. So this is great, I think, but it also it's something that's worth bearing in mind, right? It doesn't differential privacy doesn't stop you from learning aggregate information that is creepy, right? That maybe is not the kind of thing we wanted to reveal. Like maybe you can figure out which blocks have high concentrations of undocumented immigrants living on them. Maybe you can figure out where ICE employees live, right? There's all sorts of stuff that is kind of general statistical information that we think of as kind of borderline whether or not it's appropriate to be releasing this. Maybe you can, release information, we can come up with more examples if you want, but whatever. But the point is that this type of relative guarantee has to be interpreted appropriately. It's a very strong guarantee, but it still has its limits. Okay, so just briefly, there's like lots of nice algorithmic ideas out there for designing differentially private algorithms. A lot of them are based on two tools, noise addition and some sort of exponential sampling that looks a lot like is basically a special case of a Gibbs sample of the Gibbs sampling from the Gibbs distribution, if that's a term that makes sense to you. We're not, well, that's Lydia's job. I'm not going to say more than that. Okay, two things I did want to tell you that are nice about this definition that are useful and that are really useful for algorithm design. Okay. The first one is that differentially private algorithms compose. And what I mean by that is suppose I've got I'm going to run a sequence of algorithms. So I've got a big algorithm, but under the hood, that big algorithm has a bunch of modular blocks to it. And each of those blocks I prove is, let's say, epsilon delta differentially private. Even if like which algorithm I run in the second step depended on the output of the algorithm from the first step, and the third, the last one depends on the outputs of all the previous steps, nevertheless, I can prove a bound on the differential privacy parameters of the composed object. And that bound, there are a few different bounds one can prove. The simplest one is like, let's say, k epsilon and k delta. The epsilon and delta get multiplied by a factor of k, or in general, the epsilons add up and the deltas add up. But actually, there's something else more interesting going on when you're composing many, many blocks, which is that in this kind of delta world where you're allowing yourself this kind of additive slack, the scaling in the epsilon term is more driven by square root of k than k itself. Okay, so up to this log 1 over delta, we get this kind of like square root type growth in epsilon. And it turns out that type of growth is essential to the success of lots of the algorithmic strategies we use for training large models. So Lydia will say a little more about composition later. The other kind of useful thing to remember to know is group privacy. So this means what happens if I change not one person's data but k people's data, and then it turns out that the privacy parameters degrade gracefully with the larger a set of people whose data I change. The epsilon term goes with k epsilon, and then the delta term roughly grows as a factor of k by a factor of k. Although when k epsilon is bigger than 1, the formula is like more complicated. But then this is sort of, I think, at the level of the tutorial. Fine. Okay, so these two. Why are these two properties so useful? They give us a really useful kind of set of tools for modularly designing algorithms and for like looking at how kind of privacy type things propagate through a more complicated system. And so one of the most useful one of the reasons that algorithmically this definition has proven popular is because it allows you for like it allows for modular design. Okay. Well, I'll just say a little bit about how we think about composition. So, yes, go for it.
So if you change k data points, is it possible to get a square root k epsilon?
Not in general.
Reducing this to composition?
No, not in general. It depends on the shape of the algorithm. The shape, meaning the structure of the algorithm, but sort of for many, many algorithms, including like the noise addition one we saw, it's really linear in k.
I have another question.
Yeah.
Is there connection to membership group attack? Is that a thing? So you explained to us?
Yeah, well, I'll talk about that like at the sort of closer to the end of the day. But yeah, when you imagine, there's a connection here with what happens when you've got, like, let's say you analyze privacy at the level of individual records, but now you realize that one individual's contribution is really a set of records, right? So this gives you one tool for getting a handle on how much privacy degrades in that setting, and sometimes we have better tools.
And from the attack's perspective, the story, I mean, you sort of told us a story about matching the best attack with a given definition. Does that best attack exist in this?
I mean, yeah, I think it sort of depends exactly. Certainly there are ways of setting it up so the answer is yes, but probably there are ways of setting it up so the answer is we don't know. Yeah. Yeah.
Yeah, I have a question with this advanced composition in terms of the intuition.
Mm-hmm.
So for example, like people use approximate dp because of this nice property, right?
Yep.
But let's say you define the standard pure dp in a way that it's e raised to epsilon squared, then pure dp will also become subadditive, but you have really not changed anything, right? So is this like some mathematical trick or?
Oh, that's interesting. Okay, good. Let me try and rephrase the question, or just to make sure everybody's following. The question is like, is this, the difference between square root of k scaling and linear in k scaling is this just a kind of a game of reparametrizing stuff? So the answer is no, but the answer, mathematically, yes, what you said is true. You could just reparametrize and you get square root of k.
Sorry.
Sorry. What?
Explain that.
Oh, at some level, the question is a triviality. Is it like, let's say I define this, right? Let's say this is true, right? It is also the case that I can now say, well, if
Oh, if you call it.
let's call rho the square root of the square of epsilon I. Now my new rho squared is the square root of whatever the squares of the rows or something. Maybe I'm doing it wrong. Yeah. Okay. Whatever. Sorry. Okay. But just the sort of more substantial answer to your question is that you can ask, for example, for this Gaussian mean estimation, is there a difference between, let's say you're interested in a parameter epsilon equals 1, so the squaring doesn't change anything. How accurately can I release the mean? And the answer, of an arbitrary set of data points in the unit ball. And with this delta term, I can get this kind of square root of d scaling, and without the delta term, I can only get a linear in d scaling. So there's a real difference between the notions. And you're like, well, why doesn't the reparametrization fix this? Okay, we can do it offline. But believe me that it doesn't. Okay, just briefly, what's going on with composition? So one way to think about what's happening with composition is that every new output you get is giving you a certain type of information about the input. And if you kind of set up the math right, you are really adding up the information you got from each of the releases. Okay, so what does that mean? So let's define given a mechanism A and two fixed neighboring inputs, x and x prime, we're going to define this loss random variable as the log odds ratio of a given output under data set x and data set x prime. Okay, so this log odds ratio is some measure of how much more do I how much does my confidence or my belief that the true data set was x increase when I see this this output y, right? So let's say a priori x and x prime are equally likely, then this is really a Bayes factor. Okay, so now when I run an algorithm, what I'm getting is this loss, but for a random output sampled according to, let's say, x. Okay, and so this is a random variable. Right? This is the kind of thing information theorists love, right? They define a random variable that's defined in terms of probabilities. So for Gaussian noise addition, for example, when you're adding Gaussian noise, it turns out this random variable is itself Gaussian distributed. And in general, it'll have some distribution. But if I think of what is differential privacy in terms of this random variable, it is actually up to some small change of parameters, it is equivalent to requiring that this random variable be not too big with high probability, that its absolute value be exceed epsilon with probability at most delta. Okay? One of these directions is true, and the other one is approximately true. It's an exercise to figure out which is which. Okay, when you're composing algorithms, though, what's going on is that because conditioned on x and x prime, the outputs of the algorithms are independent, or rather, yeah, each condition on x, x prime, and the previous outputs of an algorithm, the new output is sort of like distributed as it should be. This sort of privacy loss really adds up. Okay? And so assuming the kind of privacy properties of the algorithms, you can choose the algorithms adaptively, but assuming the privacy properties are not themselves chosen adaptively, then composition is basically about concentration of this summed random variable, and most of the time the way we set up composition, these privacy loss things are independent. Okay, like the kinds of algorithms that Lydia will be talking about, these are set up so that they're independent. So as a result, what this means is that, like, to think about composition, we just need to think about sums of independent random variables. This, it turns out, is like a thing, right? And you can take lots of classes on dealing with sums of independent random variables, but the point is the math of this is very well worked out. Okay. So Lydia will mention, so that's just a sense of like what's going on with composition is like basically what's happening is you show that in a typical epsilon delta differentially private algorithm, the mean of these random variables is not very large. And most of the problem comes from variance. And variance kind of grows as, or standard deviation grows more like the square root of the number of terms in a sum of independent random variables. Okay. I'm torn. Okay, there's this like really nice hypothesis testing view of differential. Maybe I should say about it because it came up in the earlier part. But one way to think about this definition is it's a limit on how good a tester you can have for a particular type of hypothesis test, where you give me two data sets, x and x prime, and you ask me which one is the true data set, and I have to figure this out, right? And it turns out, and so what this is saying is that whatever test I happen to apply, it's going to have approximately the same probability of giving me a yes on the left-hand side as it does on the right-hand side. Okay? And I can think of that as sort of constraining the false positive rate and true positive rate of any test to live in some particular set. Okay? Turns out the set in this case looks like this. So there's like a little delta kind of offset here, and then this has a slope e to the epsilon. Okay? So when epsilon is 0, that slope is close to 1. It's much more, it hugs that central line much more closely, and then as epsilon increases, it grows away. And then this sort of relates to these membership inference attacks we were talking about earlier. So this view tells you that it limits the types of pairs you could possibly get. So if delta is very small, you're not even going to see the delta on this plot, right? And if epsilon is modest, you know, maybe it'll look like this, right? And so that rules out, in particular, anything in the green ellipse. And this rules it out even against an attacker who knows all the other data points, not just what distribution they come from. Okay, it turns out, so this perspective was first formulated explicitly by Wasserman and Zhou, but there's this like really nice paper by Peter and Siwoong Oh and Pramod Vishwanath, thank you, that use this perspective in a really interesting way by combined it with the sort of this Blackwell distinguishability perspective on hypothesis testing, and in particular gave like new and much tighter proofs of composition results at the time. And those are the versions that I think certainly I like to teach. Okay, and just a last thing before I hand it off. So using this definition, we do have to be careful. DP requires a notion of neighboring data sets, right? Most of the time, the right notion is kind of obvious. Like most of the time, it's sort of clear what my data is in the data set, but there's certainly cases where that's less obvious. And a lot of them come up in federated settings. Okay, so I'll talk more about this a little later. But one person could be responsible for many entries in the data set. That's one setting, right? Like, for example, I visit many different hospitals. And it could also be that each entry is about several people. Like an email thread is sort of about all the people involved in the thread. Okay? And so this requires often different mathematical approaches, entails different algorithmic approaches. The complexity that comes with this entails often different algorithmic approaches. But we'll come back to that later. For now, I'll just hand off to Lydia. All right, thank you.
Yes. Awesome. You know people are responsible. So can you hear me, or should I do something about this? Hello.
Just choose how you want to present it.
Sounds good. Let me.
Do you want to do that window?
What's the other window? Okay, let me see.
Do you want to just pick one of those?
Okay, but this is not the right one. I knew it. There's a nice that goes swap.
Yeah. It is one of those.
Okay, let me do the thing again. Okay, wait.
Is it?
We're gonna change
Is it use
standard display. Yes. Okay. Thank you. Okay. Great. Okay, so we're gonna move to differentially private training and discuss. I think my part is the what. Like, what do you learn? But the point is, we're gonna move to like algorithmic ideas on how we do differentially private training. And all disclaimers apply, like what Adam said before, like if I don't cite your paper and so on and so forth. But what I think would be interesting is, this is gonna be an overview of the main theoretical ideas that go into it. No numbers are on this slide deck. So if you go at some point, oh, this idea gave us the first deployment of differential privacy with this much epsilon, feel free to like raise your hand and say that this was a success story. But by default, this is not on the slide. So I think it would be nice if we crowdsourced this part. Okay, so this is the outline. We're going to go through the main paradigm for differentially private training, which is differentially private stochastic gradient descent. And then we're going to basically switch the way we look at this problem 2 times. We're going to look at like through the lens of continual observation and through the lens of linear queries, and then we'll wrap up. The Gaussian mechanism is the only basic building block we're gonna need for this talk. Adam talked about this. This is just a reminder for notation. So So the Gaussian mechanism adds Gaussian noise to f of x when f is the function you want to learn, and it outputs a d-dimensional vector. The amount of noise you're adding in each coordinate, the variance is sigma squared. And this is going to grow with the sensitivity, which is the delta f, the global sensitivity of f, times this other term, which basically is the log 1 over delta over epsilon term, and we're going to abstract it into this c epsilon delta term. Good. So this is the main workhorse for all of these algorithms, and it starts with, you know, the one, gradient descent. So this is a standard non-private gradient descent setting. You have some parameter space theta, d dimensions. You have a loss function that you want to optimize that takes, you know, a parameter and a data point and tells you what's the quality of that parameter or model on the data point. And then you have a data set, n sized data set, where we think that every person owns one data point for now. And this is the central model. So gradient descent goes like this. You initialize your parameter with theta 0, and you repeat the following steps. First, you get the gradient of the previous parameter of the loss on the previous parameter and on each person's data point. You compute the average of the gradients, and you take a step in the negative direction of that average with an eta scale. Okay. Standard gradient descent. Under several assumptions, typical assumptions, the loss of the average iterate at the end, or like the sum of theta t's for t1 to capital T, is smaller than the best loss you could possibly get, plus 1 over square root t. And so the typical result under some assumptions looks like this. This is very small, I'm sorry. You get this extra term that depends on eta and t. And you choose eta so that the sum is minimized, and this gets you the 1 over square root t convergence. Good. How do you make this algorithm differentially private? The purple ones are going to be the changes. So differentially private gradient descent was first used and then tightly analyzed in the first and the second paper. These are the changes you're going to have to make this algorithm differentially private. First, each gradient has to be clipped. This means that you have an operator, and it can be the one that I have on the slide, it can be some other operator, but somehow you have to make sure that the L2 norm of each gradient is bounded by some parameter c. One way to do this is to reduce every coordinate by c over the L2 norm of the vector. There are other ways to do it. So the first change is clipping the gradient. And then the second change is using the Gaussian mechanism to release this average of the gradient. So instead of releasing the average as it was before, you add Gaussian noise with 0 mean and sigma squared variance in every direction. And then you use this noised average in the update step. Good. So what's the privacy guarantee of this algorithm? These steps are going to be differentially private. The Gaussian mechanism step is going to be differentially private, as long as I add enough noise in each direction. How much does the Gaussian mechanism tell me I need to add? The Gaussian mechanism says that in each direction, I need to add noise that scales with the sensitivity of this gradient average times this factor of c epsilon delta that we mentioned before, this log 1 over delta over epsilon. So what's the sensitivity of the average? Since I've clipped the gradients, this average can change by at most c over n. right? And so the noise I have to add scales with C over n times the log 1 over delta over epsilon factor. And so if I do that, I know that this step is, the round is differentially private, epsilon delta differentially private. Does this make sense? Okay. So I know that theta essentially in every round is differentially private because it's a post-processing of this average of the gradients. So I'm not using the data, I'm not doing anything else. Good, so every round is epsilon delta differentially private. By advanced composition, which we just saw, the whole thing is square root t epsilon t delta differentially private, right? Because I'm doing t rounds of epsilon delta differentially private mechanisms, adaptive composition. And so this means that if I want the whole thing to be epsilon delta differentially private, I need to readjust my epsilon and deltas here so that the total is epsilon delta and not square root t epsilon t delta. So what I have to do is to essentially add noise in every direction, in every round, that scales with square root t over epsilon, square root of log t over delta, times c, the clipping parameter, over n. Good. So now this algorithm is epsilon delta differentially private. Its utility under kind of the convexity, Lipschitz, and smoothness assumptions that I'm hiding changes, of course, because I've added now some noise. And how much does it change? Remember the first two additive errors were coming from just regular gradient descent. The last thing is what I'm paying because I'm adding noise in every round. And now I need to readjust my etas and t's so that I minimize all three terms. And what I get if I do that is an extra additive error that scales with square root d over epsilon n. Okay. Yes?
Is there a log t in the third summit?
There's definitely logs that I am,
I
yes.
was just wondering if it, like, because of this accounting, you don't necessarily get.
Oh, yeah. That's definitely something we're going to mention. Yeah, you're right. For now, yes, there's a log in the third term that we're missing, log t over delta, which can go away. Yes?
Do we assume anything about the clients or the user functions being related? How do you ensure C doesn't show up at all?
C does show up.
C? Okay, I see.
I've
It
just
is-
scratched it away. You're right. Yes. So like C goes in front of the square root d term. As we move through the talk, C is going to be 1. I think that's why it's not there. But yeah, it's an important parameter. What is there something else? They don't have to be related. The gradients of each client don't have to be related. They just all are bound. Each one is bounded by L2 norm at most C. Yes.
Like, I guess it's not theory, but in practice, is it more usual to use L2 norm or like some other norm?
I don't know. I think that's a great question, and also like an asterisk that I want to mention is we're not talking about how, like we're not going to talk about how you find C and things like that. It's super important. Like you have to know to not over bias or over noise the gradient. But if you have if someone has other comments on like what's used in practice in terms of clipping.
C equals 1 is pretty popular.
C equals 1. There you go. Yeah. So, okay, any other questions?
So these assumptions that you have mentioned are on the step size or?
No, not the step size. I mean that you can assume that the function is Lipschitz, the loss function is Lipschitz, and the data space is bounded.
But basically, the noise addition that you do is kind of adding more variance into the batch gradients, right?
Yes, the noise addition is what driving the error, basically, here. Yes, Mariam? No. No, okay, sorry. Yeah.
So the assumption here is that the function is Lipschitz, or is it also possible to give
I'm
this under
doing a
smoothness?
very crude presentation, but here I think the basic thing is if you are not doing anything bad by clipping the gradients, then this goes through. Like if everything is under C, if the gradients all are under C, like L2 norm C.
I see. So, okay, so then you need like bounded gradients almost.
Yeah,
okay.
or some other equivalent, exactly, notion. Like bounded domain and Lipschitzness. Yeah.
I see. So, is it known how to extend this to the smooth setting where you have bounded, not bounded gradients, but like Lipschitz gradients, or that's
There are a ton of works that consider any variation of like smoothness and convexity, strong convexity, Lipschitzness, continuous gradients. Okay, let's move ahead. Good. So this is dPHGD. It's epsilon delta differentially private. The error it gets to is the square root d over epsilon n. The only bad thing about it is its running time. Why? Because in every round, you're computing n gradients. And so you're doing this n times the time you need to compute a gradient in every round. This is the main driver of the bad running time, or like slow running time of dPHGD. And the next question would be, okay, can we do this faster? And there comes stochastic gradient descent to solve this problem. And so basically, stochastic gradient descent does the following. The only change, again, from the previous slide is the purple line. In every round, I'm sampling one user, like one gradient, uniformly from the n users of gradients that I have. And I'm clipping that gradient. I'm only using that gradient for my update. And so the running time changes so that in every round, I'm computing one gradient. And d is just the time to find the, to do this addition of like vectors, d-dimensional vectors, which can't go away. But the point is that n is not there in the running time of every round. Good. So why don't we, also asterisk, it doesn't really have to be one user. It's okay if it's a few users, in which case you do what we call batch gradient descent. But in any case, like the number of people you involve in every round is gonna go into the time in every round. Good. So differentially private stochastic gradient descent. Why can't we move to this algorithm? Yes?
You were going to say this, right? The noise would blow up.
So exactly, right. So I didn't change the noise from the previous slide. So this was the noise that we were adding in like normal gradient descent, no stochastic gradient descent. But the sensitivity of this step is actually now C. So like I'm not averaging, so it's not C over N, it's C. Which means that you can look at it this two ways. If I keep adding this noise, then the privacy of this step is n times worse than it was before. Or I should basically delete the n from the amount of noise I'm adding and increase the noise I'm adding by n in each coordinate. So that's a lot, and it would ruin the accuracy 100%. And this huge idea comes along that helps us avoid this step and make SGD usable. And that's the idea that's called privacy amplification by subsampling. There are perhaps, okay, so this is the statement. Imagine you have an algorithm, A, that's epsilon delta differentially private. Now also imagine you have a function, S, that basically all it does is from an n-sized data set, it's gonna choose each user randomly with probability p. So it's a subsampling procedure. Now, if you first use S to pick a subsample, and then you use A, the composition of these two algorithms, A composed with S, is this much differentially private. So the new privacy parameters you get are log of 1 plus e to the epsilon minus 1 times p, and delta changes to p times delta. And to interpret it as this a little bit easier, if epsilon is small enough, this basically means that the privacy of the composed mechanism now is much better by p. So epsilon and delta are now p times epsilon and p times delta, and remember p is smaller than 1. It's a sampling probability. It's with what probability am I going to add this person to the subsample. So this private simplification by subsampling is a really big idea. Intuitively, it's also really nice, right? Because if you don't think about this way, then basically it's like you're saying, okay, there's a situation where one person's data point comes in every round. This is not going to happen, though. With, in expectation is going to come in only in one round. And you're adding, the other way to look at it is you're adding more randomness to the process so that the adversary doesn't know whether one person's data point was used or not. And so overall, remember we had this much noise, but the privacy was n times epsilon and n times delta in that case. But now basically, if I choose probability p equals to 1 over n, then basically what happens is that I bring back my epsilon and delta to the scale that it was. And so the whole thing with this much noise in every round is epsilon delta differentially private. Yes?
Do things change if you just secretly shuffle the data set and go over it in order, like sampling without replacement?
So it's a really good question, yeah. So we're going to talk a little bit about the challenge in sampling in a few slides. But yes, things change depending on how you decide to pick the batch or the sample.
So far, it's sampling with replacement uniformly.
Yeah, the best, the cleanest theoretical analysis, I would say, is Poisson sampling, where every person gets a probability p of being sampled in every round, which also gives you a variable size batch in every round. So this is the cleanest. But there's sampling with replacement or without replacement. There's what you said, like shuffling and going through the data set in a row. Yeah, so it varies. The guarantees vary. Yeah.
So does the following idea make sense? If I'm trying to implement SGD, if I add noise inside the clipping operator and then add noise outside as well, is it possible to look at some probabilistic notion of sensitivity and then maybe use this to...
If I add noise in the clipping operator?
Inside the clipping, on the gradient, and then do the clipping.
How much noise would you add in that case?
I don't know, some noise, which basically just makes maybe the sensitivity a bit moderate or something. But
I can't
it's not worst case sensitivity, so it need to be maybe some...
I can't see how it helps to...
Oh, you can't?
You need to add noise in this step.
Yeah, you still add noise here, but
Okay.
you also add noise inside, which will control the sensitivity of G bar D. Maybe that doesn't make sense.
Maybe let's take it offline. I don't see how adding more noise before the clipping is going to make things better. But maybe, yeah, let's take it offline if you don't mind. When should we stop? Okay, so how does this sound? Maybe we go another 20 minutes? No, too much. Okay, let's do until like 12:15, and then we'll figure out what to do in the next part. Okay, so the takeaway is that DPSGD is great with this privacy amplification fix. It's epsilon delta differentially private. Its utility, like we didn't talk about this, you're doing one gradient in every round, not the average of all the gradients in every round, but because the thing that's driving the error is mostly the noise because of privacy, it gets you roughly the same utility guarantee. So it's still square root d over epsilon n over the best theta star in theta, and it runs much faster than DPGD. Good. How can I make it even better? Well, the advanced composition result that Adam talked about is tight. But it's tight if you think about like black box mechanisms. You have this epsilon delta mechanism, and you're composing black box epsilon delta mechanisms. The thing about DPSGD is also we know exactly what the algorithm is. So maybe the thing you should do is track the privacy loss a bit better. And this is where this huge line of work that's called privacy accounting comes in, with the first one being the so-called moments accountant, where the idea is you take the privacy loss random variable, you take the log moment of that random variable, you show composition results for that, and then you convert it back into epsilon delta differential privacy. So this turns out, for example, if you put this type of composition analysis into DPSGD, it turns out to remove the t from the log t over delta term in the noise that you're adding in every round, which means that overall you're getting this improvement on the noise. There's a rich literature in this type of work, and the moments accountants was kind of like an inspiration of Rain EDP. It was a numerical approximation to track the privacy loss. Then other works after that found some closed form bounds. Other works analyzed fixed batch size sampling. Later, there were works that used the full privacy loss distribution. So you have the privacy loss random variable. You don't just look at the moments. You look at more information about the privacy loss. And last but not least, kind of this Gaussian DP approach of hypothesis testing is really tied to the Gaussian mechanism, and it gives you even more tight bounds on tracking the privacy loss if you use this type of approach. The bottom line is that you can do composition or tracking the privacy loss in these types of algorithms better, which gives you huge practical advantages compared to the thing I presented in the beginning. Yeah, and I think that's a good, okay. That's a good spot to get, yeah, let's do more questions and then we'll continue after. Yes, Maddie.
Yeah, I mean, it's like a question. Probably you know the literature, that's what I'm asking. So, like, when I numerically played with DPSGD, and one of the painful parts is that you need to commit to the number of iterations, then you need to choose the noise, and then you need to run. And then what happened in practice, you run it and say, oh no, it's not good enough, let me do it again. And people sometimes they don't pay for
the extra rounds.
So there's this literature in convex or maybe optimizations that anytime algorithm in which you kind of want that whenever you stop, you get the best you want. Do we have such a result in the private optimization that we don't need to commit to a number of steps beforehand?
Yeah, like the stopping time being dependent on
Right, for
the
example.
data.
Yeah, it's a very vague
I actually
question.
don't know. Yeah, I think it makes a lot of sense. Like, do odometers kind of do this? Privacy odometers, or yeah, I'm not sure. Yeah, good point. Peter, was it on this question?
No, I was going to ask you about something else.
Oh, okay. Then I think maybe Sebastian.
Yes, Sebastian. Okay, thanks. I have just one short question. Also, I think you explained very well how this, from a privacy perspective, works. When we look at optimization algorithms, we somehow, when we want to compare them, we always ask the question, oh, for a fixed level of accuracy, how many steps of my method do I need to do?
Mm-hmm.
And I think on one point on your slide, you changed the accuracy
To
from
D.
epsilon to square root d over epsilon. And
Yeah.
does this mean you would need to do more steps?
I think the steps are like n squared over d. Yeah, so at some point we picked the t that's going to minimize the privacy noise. Otherwise, where's my, I need my pointer. Okay, so otherwise I think you get, sorry. Yeah, you can decide what to do with this noise here, or like, yeah, not just noise, with this error, or like regret. You can decide how to optimize it, but the fact that t shows up here is a big change from the first two terms. So I guess, yeah, I'm not sure how, if you wanted to talk about accuracy in terms of t, or t in terms of accuracy, you'd have to switch this expression.
Okay, thanks.
Yeah. Yeah.
So, two questions. The answer to the first will depend on will determine whether the second question is relevant or not. Is this known to be tight in any setting for like a class of functions?
Yeah,
For
I think,
whatever class functions you're analyzing this for?
yeah, I think the square root d over epsilon n is.
I see, but the entire rate is known to be tight, like the convergence rate with the accurate privacy term. Is that entire thing known to be tight for that particular class of functions with private optimization, or?
I'm not. Wait, doesn't it mean that picking the best eta and t in the first, if picking the best eta and t in the first expression gives you the tight bound, then.
Yeah, but here the trade-off changes, right? Because at least it seems it changed. I don't know why there's not a third term in the last thing you wrote, but there should be probably. And there's a t in the numerator, so something you've done has
I've
changed the
picked
trade-off.
eta and I've picked t
So pick t, okay. But
to minimize.
where does the optimization error go? Where did the optimization error go? Or
So the first two terms are
merge in
the
last
just
term. I see,
normal
I see.
without privacy, and the third term is the error because of privacy.
So
Yeah.
is it known that this is the best function suboptimality you can get for this class of functions for this level of privacy?
I'm not sure, but I guess I'm trying to say, if the square root d over epsilon n is the best thing, and you're getting that by fixing eta and t.
And in terms of
And sorry, also, actually, no, I take it back. We're gonna show much better algorithms. So I guess
okay.
there is, yeah.
Okay, then my second question was, when you're adding this noise to g bar t in step 2, does it make sense to exploit that you are actually reducing gradient terms over time? Because you're getting closer to the optimal solution? Or you want to use like a constant clipping based bound and then you can't get anything better with?
I see. I think there's a literature in adaptive clipping, which we're not mentioning for now, yeah.
But it gets you some like improvement or in some regime, or?
I'm not sure if it's significantly, like compared to the other algorithms we're gonna show, which really get you a bigger improvement. I'm not sure if adaptive clipping is getting you as much as the next frameworks. Okay. Yeah.
Yeah, if you go to the slide with DPSGD with subsampling amplification.
Mm-hmm. Take this.
Yeah, here. So it seems that DSF3 is a sample gradient, right, or batch gradient?
Is one sample. In
One
this case,
sample.
it could be a batch.
So that's
Both.
sigma shouldn't be C over 1 now because it's no longer on data set, it's on one sample.
Yeah, I didn't change the noise from the previous round, and what I'm arguing here is that if you leave it like this, then the privacy of this step is n times worse.
That's it.
Like you can think that the epsilon of this step is n times epsilon. The point is that this is fine, this amount of noise is fine because of amplification, but as is, it's not, because the sensitivity of this step is C, but I'm adding noise scales with C over n. So it would not be private if it stayed, without the amplification step. Yes?
So, you said if we explicitly use the privacy loss random variable, we can do better than advanced composition, depending on the mechanism.
Mm-hmm.
And so then assume Gaussian mechanism will get you the best composition. Is that right?
Gaussian DP?
Yeah.
I think it's the tightest.
Okay.
But, I mean, I don't want to seem unreasonable. Like, the square root T is there, right? But you can improve a lot of other terms, which in practice, I guess, help a lot. Even if, yeah.
If we make an assumption that the gradients are Gaussian distributed, is there a chance for us to improve something here by using some of the mechanisms that I think you've also contributed to?
Yeah.
I know that maybe runtime-wise, there might be some computation complexity issues, but theoretically, can we improve something here?
That's a really good question. I don't know. In the next parts, I was thinking of drawing connections back to this because we were going to talk about Gaussian averaging. So in principle, if you do assume that the gradients are Gaussian, and if you're okay, the algorithms are, like you said, much more complicated. Like the running time goes up, then you could possibly get things that use second order information for free. The theory hasn't been tested, but in principle, you could use second order information for free and also do sometimes. The other thing is adapting to the subspace, which there's an approach that says you can use public data to find the subspace, like a lower dimensional subspace when the gradients live, and then do gradient descent with that, which would be nice. But what if you didn't use the public data to do this? If your data were Gaussian, then you could possibly do this without public data. But I'm not sure if it's really viable. But I think it's really interesting to entertain the idea. I feel like I should let you go to lunch, and if people have more questions, we can. I'll stay for a little bit.
Let's come back at 2.
Yes, that would be perfect. Thank you.